Hello, welcome everyone to Zahid's data mining channel once again. My name is Zahid Islam. I'm a professor of computer science and also serving as the Associate Dean Research in a faculty at Charles Sturt University in Australia. So today I will introduce our very recent paper, a very recent paper from us on privacy preservation while collecting data from survey participants. So let me share my screen quickly. Okay. So I hope you can now see my screen and it's being recorded. So this is the paper. The title of the paper is UDLDP, a technique for optimally catalyzing user-driven local differential privacy. And these are the authors you can see. The lead author was our very beloved PhD candidate, Yana Kumar Thed-Channamurthy. And the co-authors are Professor Tanveer Zia from Notre Dame University, Australia, Professor Maisam Mohammadi from Iowa State University in the United States, and Dr. Michael Biang and myself, Zahid Islam, from Charles Sturt University. Yana was a PhD candidate at Charles Sturt University. And this project was funded by the Cybersecurity CRC in Australia. Now, the paper, you can see the front 2 pages of the paper. UDLDP paper, and this paper was published in Future Generation Computer Systems, a very renowned journal. Also, a preprint version of the paper is available on in SSRN. So you can download the paper from the journal, and that is the final version, and also a preprint version is freely available that you can download. This future generation computer system, in terms of core ranking in Australia, core 2020 is the latest ranking for journals. And in terms of that ranking, it is ranked A, just below A star is A, above B. And in terms of SJR ranking, it is a solid Q1 journal with a with an impressive H index of 164. Now, let me introduce the paper. First, let me talk about the scenario. Let us imagine that a Department of Health is aiming to understand the distribution of health conditions in a country over different states, towns, regions, etc. The health conditions such as diabetes, how many people are diabetic and how many are not, or how many people have cardiac disorders and how many do not have similarly respiratory conditions, etc., within specific locality across the country. So it's a scenario, and let's say the purpose is to understand how they should most effectively allocate their resources. So if they know that the concentration of diabetic patients is high in that particular region, then maybe they need to equip those service providers, service facilities in those regions accordingly. So they need to understand this distribution very accurately so they can actually take necessary steps. Now, in order to achieve this, they need to run a survey, right? They need to ask that population in those regions residents suitable use yes no type questions about their health conditions in this particular scenario. But the problem is the individuals, I mean, this is the interest of the health department, but the individuals may not be quite comfortable in disclosing their private information, like whether they have, let's say, sexually transmittable disease or not, whether they have serious health issues, in particular, like HIV positive or not. Some of these questions to some of these participants can um, look very sensitive, may appear to be very sensitive, privacy sensitive questions, and therefore they may not want to participate in this survey. So therefore, we need a system that can ensure the survey participants that their privacy will be preserved, but at the same time, the data collectors will receive good quality data so that they can estimate reasonably accurately the distributions, heavy hitter, correlation among different survey questions, and so on and so forth. So to do that, we are proposing a technique called UDLDP, user-defined local differential privacy. Local differential privacy is a type of differential privacy approach for privacy preserving data sharing, data mining, data distribution, data access, queries, etc. But local differential privacy is instead of the whole data set, it's a one-to-one kind of queries and data collection. It can be used there. So our technique is user-defined local differential privacy. Let me first present and introduce our technique, and then we can see how it differs from the existing approaches. Now, this is a scenario. Let's say this is the Department of Health, and these are the participants. Now, they want to collect this information from the participants. They want to know whether participant 1 is, let's say, diabetic or not. Do you have diabetes? Participant 2, do you have diabetes? And 3, and so forth. And these participants are happy to share that information provided their privacy is maintained, is preserved. Now, we understand that because of the ethnographic composition of these participants, they may have, due to their culture, due to their demographic background, education background, due to the types of question being asked, they may have different levels of privacy needs and privacy sensitivity. Now, in this paper, that is the main contribution, that we are trying to cater for individual privacy and get the best data that we could. So let's say this Department of Health is asking a question, do you have diabetes? So what it does, these are the steps, S1, S2, C1, C2, etc. And in this table below, we are actually explaining the steps and the little bit of description of what happens in those steps. And I'm going to explain it very quickly anyway. Look, the purpose of this presentation, I want to keep the videos short so that it doesn't become too boring, but at the same time useful enough so that you get the initial idea about the paper, and then when you go and read the paper, it makes a lot better sense to you. So that's the purpose. So let me try how quickly I can give that initial clear understanding so that then you can actually go read and enjoy and understand. So first step is S1, and S1 is optimized cohortization. By that, we mean that what we mean is instead of assigning one single epsilon value for privacy, epsilon value for privacy means in local differential privacy, lower epsilon means higher privacy. So that means the answers of the participants choosing a very lower epsilon value um, will be heavily noisy, heavily modified. So, and the higher epsilon value means the noise, amount of noise added to the original response will be low, will be less, and therefore the data will be more useful. So it is better to, from the Department of Health's point of view, it is better to use a high epsilon value so that they get more clean data. But from the participants' point of view, they need the epsilon so that it preserves their privacy. And some people may be very privacy sensitive. They will need lower epsilon value. They will prefer. Some people are not privacy sensitive. They may say, oh, I don't care if I have diabetes or not. I'm happy to tell you. So they can choose higher epsilon value. So there is no one epsilon value that's one size fits all, so that sort of thing. But the conventional approaches will choose a single epsilon value. And guess what? Which epsilon value they need to choose to bring the maximum number of participants to the survey so that they participate in the survey. They will, of course, have to choose a very low epsilon value so that it can satisfy even the very conservative group of participants who are very sensitive to privacy. So if they are satisfied, then people who are not that sensitive, they will also be satisfied. They will say, I was not that sensitive, but well, you are preserving my privacy that well. Okay, that I don't mind. Okay. But at the cost of quality of data. The Department of Health is getting lots of participation in the survey, but the quality of the data they are getting will be very noisy, will not be as good. So, and then the reconstruction of the distribution will not be as accurate, right? Because the person one said, yes, I have, it's changed to no. Person two said, no, I don't have, maybe with a probability it will remain no. Person three says, no, I don't have, it will be changed to yes. So it's very random and we don't know what's happening. So that is why we say that we will give epsilon options to the participants. For example, they can choose epsilon 2, epsilon 2.5, 3, 4, 5, whatever, up to, let's say, 32. Then, and a question may arise that how do they know what is epsilon? Maybe we can translate it like in different ways, that are you extremely privacy sensitive to this question? Are you reasonably privacy sensitive? Are you not privacy sensitive? Are you not at all privacy sensitive, etc.? And those different categories may indicate different epsilon values. So they can choose their category and they will get their interests protected. So that is the first step, that we identify a number of epsilons. We may imagine that this is what we are saying, cohortization. We may imagine that this population can be best divided into 3 categories or 5 categories or 4 categories. And based on that, we may provide different epsilon values. And the paper, if you read the paper, you will get a better idea about this. I'm not going into too details because then the video will be too long. So you get the initial idea. So let's say we are, okay, so why we want to do that? First, let me explain that because this figure came up. Why we want to do that? We want to do that because imagine if we are, this is the United States and this is color coded, let's say, concentration of diabetic patients. Let's say, I don't know, darker color means more. It's a symbolic figure only. And and lighter color means less diabetic patients. Now, if we use one single epsilon, which is, let's say, very conservative, then the answers of the participants will be very distorted, very modified, very perturbed. And then, though, based on that, when we reconstruct, our reconstructed values can be quite useless. And based on that, if the hospitals or Department of Health wants to allocate resources, that resource allocation may not be as effective. Therefore, we are saying, let's give the opportunity to individuals to choose their epsilon. And what we are doing here in step one, instead of giving one single epsilon option, we are, in this example, we are giving 1, 2, 3, 4 epsilon options, right? These 4. So one is 15. You can choose 15. Maybe it can be interpreted in human interpretable language, like I'm not sensitive at all. I don't care. I'm reasonably sensitive, but I don't mind. It's 12. I'm quite sensitive. I'm extremely sensitive. That's 2. And quite sensitive is 8. So something like that. I mean, that's the application side. But in this paper, we are saying that, okay, we will give epsilon options. Now, let's imagine there are about 12 participants in this survey. Just an example. And participant 1 thinks that their epsilon preference would be 16. And therefore, they will choose the most closest option, which is just below 16, as the most suitable option for them. So their epsilon requirement is 16, means they are not at all sensitive, possibly. But the highest value in this option list is 15. They will say, okay, it preserves my privacy. I don't mind. I will choose that one. Somebody may have an epsilon choice of 14, and they may say, oh, 12 is the best option for me. I will choose 12. They will not choose 15, because if they choose 15, then it is not quite satisfying their privacy needs. So they will choose 12. Similarly, if somebody is 7, they will choose 2. Somebody is 5, they will choose 2 as well. So this is our step 1. Then in step 2 is transfer the epsilon value and Q1. So basically, step 1 and step 2 are a little bit, overlapped here. And you can actually, in your paper, you can say that this table actually does not provide, the sequence as they are actually explaining in their paper. So, but the basic thing is step 1 and step 2 is like kind of overlap. So step 2 is we have this question and the option of epsilon, we send it to the clients, the participants, and then participants choose this most suitable epsilon values for them. After that, then step C2 is the coding. Coding means now, based on these specific epsilon values, let's say participants 1's answer was yes, 2's answer was no. Now, based on these specific epsilon values, the original answer, yes, which is 1, and no, which is 0, may get changed. Okay, so some of the yeses will be changed to no's, and some of the no's will be changed to yes, something like that. So as I said, like if we allow this user-defined epsilon, then you can see in this figure that every user can choose their epsilon as needed, and therefore the people who are not sensitive, their data will not be modified so heavily. So it is good for the Department of Health or the survey data collectors that they are getting good quality data and without harming anybody's privacy, because those people are not so sensitive. Who are medium sensitive, their data will not be modified as much unnecessarily, because they are they are not super sensitive. So their data do not need to be modified like the data need to be modified for the super sensitive people. So still better than where the survey collector is getting data quality better than the other option, choosing the most sensitive group's epsilon value. So therefore, they are getting better data, and as a result of that, their reconstruction estimation of the distribution of diabetic patients in different states will be more accurate. It will be more accurate to the original distribution. And therefore, the purpose will be served better. In this example, resource allocation, they will be able to do better resource allocation. So this is what that epsilon, user-defined epsilon does. And then the next step I want to show you is how that noise is added. So as I said, like coding and then noise added. So let me explain this coding bit a little bit. So let's say the answer can be yes or no. Now, if the answer is yes, let's say it is coded as 1. And if the answer is no, it's coded as 0. So we can see 1, 0, 1, 1, 0, 0. So these are the original responses of the survey participants. Now, the responses gets perturbed. And how do they get perturbed is this. So there is a perturbation probability f, and this f is if we can use different techniques. Here we are using for example, in this example we are using basic rapport, and this but this basic rapport is not the only technique that we could use, but in this particular example, we are using basic rapport, which provides local differential privacy. So according to that, the probability for data modification f is 2 over 1 plus square root of e to the power epsilon. Now imagine epsilon value is 0. So e to the power 0 is 1. So square root of 1 is 1. So 1 plus 1 is 2. 2 over 2 is 1. So probability f of data being modified is 1, means definite. Okay, 1 out of 1. So that means data will definitely be modified. So that means the highest level of privacy being provided. So whatever you say, your data will be modified, something like that. Now, how it gets modified? So the coded data, that means, yes gets coded into 1, no gets coded into 0. So that 1, 0, 1, 1, those coded data is replaced by 1 with a probability of f over 2. So in this case, if f is 1, if epsilon is 0, which is the highest privacy, then 1 over 2 is 0.5. 0.5 probability means 50% chance that the coded data will be replaced by 1. Note that regardless of the original coded value, so whatever the value you have, either you have 1 or 0, I don't care, it will be replaced by 1, regardless of your original value. So that's complete random, right? There is no connection to the original value. It can be changed to 1 and by 0 with probability f by 2, which is 1 by 2 is 0.5. So if epsilon is 0, then 50% chance that whatever your original coded response be, it will be changed to 1, and 50% chance that it will be changed to 0. So imagine if you have 100 participants, ideally or most probably, you will get 50 ones and 50 zeros. And that has nothing to do with the original responses. So this is pretty useless data, right? But it gives theoretically the maximum privacy. Of course, it gives. That's why epsilon is 0, means highest privacy. And that's why in this example, we did not give 0 as an option, because then it's of no use, right? So that data. And So this is that, and then coded data remains as is according to this one basin rapport technique, as is with a probability of 1 minus f. So that means coded data, if it was originally 1, it will remain 1. If it was originally 0, it will remain 0 with a probability of 1 minus f. What is f? F is, in this case, if epsilon is 0, f is 1. So 1 minus 1 is 0. So that means coded data remains as is 0%. So originally, the data does not remain as is. Now imagine if epsilon value is very high, let's say 32, then it will be the other way around. Then f value will be low. The higher the epsilon value, lower the f value be. Let's say for some case, f value is 0.2. So that means 20%, right? So in that case, 10% chance that the original value, coded value will be changed to 1, and 10% chance that coded value will be 0, will be transferred, modified to 0. So 20% gone, 80% chance that the original value will remain as is. So for 100 participants, for 80 of them, you are getting exactly original response. You are getting much better data. For the remaining 20, you are getting pretty much noisy data. It's either 0 or 1, regardless of their original response. So lower the F value, better your data quality. And to get lower F value, you need high epsilon value. So this is that sort of thing. So this is how we reach to step C3, that the perturbed code Ri prime gets changed from Ri. Now, step S3 and C4 is then the participants, survey participants, actually share these data to the Department of Health. They collect that data. And now they know that there are 4 cohorts. 4 cohorts meaning there are 4 different sets of epsilon values. And what they will do, they will try to reconstruct the distribution for each of them. In this case, distribution being the number of yes responses, right? How many people have diabetes. And that way I can see that which cohort has what sort of diabetic distribution, and then I can find the total distribution for the whole group of participants. Now, how we do that is, so we can actually get these responses, and we can say this is C1 group. This is this green is like not privacy sensitive at all. Blue is moderately sensitive. Yellow is quite sensitive, and red is very sensitive. So these 4 groups, and then we know that this group has epsilon value greater than 15 because 15 was the option given. So they had 16, somebody could have 17, somebody could have 18, whatever, they are more than 15. And they have chosen this, and the total count value of the perturbed values for this group is 1. For this group, the blue group is 0 plus 1 is 1, and so on and so forth. So yellow group 3 and red group 3. So this is the noisy distribution that the Department of Health will receive. Now they need to try to estimate what was the original count values. So they can see that, yes, we are getting 3, but the epsilon value was used by this group was 2. Now they try to estimate what was the original value, and they will estimate the original value was possibly 3.5. Maybe out of this 1, 2, 3, 4, 5 people, about 3.5 people said yes, they are diabetic. The actual answer is 2, right? Original value is now 3. Original was 3, 1, 0, 0, 1, 1. There are 3 ones. The perturbed value is 0, 1, 1, again 3. But then they are estimating 3.5. So it's not as accurate estimate. That's because the epsilon value is very low. On the other hand, when the epsilon value was quite high, let's say when it is 12, see the original count was 1, and their estimate is 1.0001. It's almost 1. So their estimate is more accurate. That's because the epsilon value was high. And how that is happening is by this equation. If you read the paper, you will get a better understanding of these equations, how to recalculate the distribution. SI is the count in the bin in this category. For example, if we consider this one, the epsilon 2 group, C4 group, then count value is 3. So SI value for that group is 3. NI is the total population in this group. There are 5 people. F over 2 is that F that was used for epsilon 2. We will get a F, which is pretty high because the epsilon is low. And then 1 minus Fi. So by that way, I is the ith cohort, like here for C4, I will be 4. So we will get an estimate, and that Ti value will be 3.586. So once we get all these reconstructed counts, then finally we can calculate the final count, which will be 8.6. So they know that they surveyed 12 people. Out of that, about 8.6 people are diabetic and 3.4 people are not diabetics. Now let's see the original answer. 1, 2, 3, 4, 5, 6, 7. There were 7 people diabetic. So their estimate of 8 or 8.5 is pretty close to the original distribution. Now, the more people they survey, possibly their accuracy will get better because there will be more people with less sensitivity, and the population size will be big, and their estimation will be more accurate. So this is the basic idea of this technique. And then I said that how it differs from existing local differential privacy techniques, like the basic rapport technique, for example. They would provide 1 epsilon value only. And the problem with that 1 epsilon value, as I said, is if they use only a single epsilon value, that has to be very restrictive, very low, so that it satisfies even the most conservative people there, and therefore their reconstruction will be not as good and maybe not as useful. So that is the problem there. So they will use 1 epsilon value and they will get response from the participants, and participants will have no option. But the main difference is we are giving different epsilon values. Now in this paper, we have also tested this with, as I said, like rapport is just one approach, one technique that we can plug into our framework, into our solution, but we could use other techniques. And in this experimental evaluation, we have used randomized response, count, mean, sketch, etc. And we compared our UDLDP with classical LDP approach. And then we also used real world and synthetic data sets. We did a trick here. We used the adult data set, which is available, which can be downloaded by anyone, publicly available in UCI machine learning repository. And that data set has 2 different, many variables. 2 of the variables are gender, male or female, and salary greater than 50K or less than 50K. So we thought we'll be asking these 2 questions as one by one as participants. Are you male or are you female? And from other studies, we know the privacy sensitivity of people among the sensitivity among the males, females, and no, that data set also had age. I think yeah, I have to admit that I'm telling you off top of my head, but when you read, you will remember, you will see the more details and more accurate information. The dataset also had age, and I think based on age, gender, based on educational background, there are other studies that the expected privacy sensitivity of people with these demographic information. So we use those criteria to simulate a privacy sensitivity of those people, and therefore they will choose that sort of privacy sensitivity, etc. And this is just a experimental setup. It's nice. It's nice design, experimental design. And then we checked histogram reconstruction, how accurate histogram reconstructions are for our technique, UDLDP, as opposed to classical LDP. And then heavy hitter also estimation. So which is the most common one if the categories are more than two, correlation analysis, etc. And we can see that cohorted means our approach, UDLDP, because we are using cohorts. Our absolute error rate is percentage is lower than non-cohorted, and also the standard deviation is also lower than non-cohorted, and that is for gender and also for income. So that's basically the main idea of this paper. I hope you will now read the paper, and then that will make a lot better sense to you, and you can find flaws of this paper, just modify it and publish your paper. For example, you could I don't know, you could try number of cohorts. Although we have done some experiment on that as well, the impact of number of cohorts. If you have one cohort, then you have lots of people in that cohort. That will help you to get better accuracy, but then you are compromising your privacy sensitivity. You are choosing a very low privacy option, epsilon value. But you may have many cohorts, and you could cater for almost everybody's need, but then within each cohort you might have low number of people. So those kind of things you can test, and I hope you will enjoy the paper. Thank you very much. Thanks for watching, and I will stop sharing. And that's all. I will stop recording as well. Thanks for watching. Enjoy the paper. Bye.